Thanks for the nice introduction, and I would also like to thank the organizers for this opportunity to speak here, and for all of you here to take your time to attend my talk. So without further ado, let me just say what I'm about today. So very long title, not to worry. It has, the results are very rich, but I'll try my very best to distill it in the simplest manner possible so that you can take away most, as much as you can from the talk. Okay, so let me just go to the outline. I'll first give you an introduction and motivation why we started. Okay, with some history of some previous work that we have done and how it all led to this particular work. And then I'll briefly go through the calculation methods that we use. These are very simple, straightforward physics calculation methods. So I have to emphasize that these are physics calculation methods mostly. Okay, so this is these results are physically derived. They're not using rigorous mathematical methods, but what we hope to do in this project and this piece of work is to give some predictions from mathematics from physics. Okay, and then I will introduce to you two topologically twisted 5D n equals to 2 gauge theories. So in 5 dimensions for n equals to 2 gauge theories, there are two distinct twists, fully topological twists, meaning they are topological in all 5 directions. Only two possibilities. Okay, I will introduce these two fully twisted theories to you. Of course, if you have twists which are not fully topological, meaning they're holomorphic in 2 directions, topological in 3, you can have other combinations, but if it's just fully topologically twisted theories, you only have two distinct ways of twisting 5D n equals to 2, and I will introduce those two theories to you, and they will feature in our work. And then I'll go on to the results. So this results section is in some sense a summary of the results, okay? So that you have a big picture of the results that we've obtained. I will go through them, and if time permits, I will go through the details in the appendix. I will select some details to go through. This appendix is pretty exhaustive, so because the slides will be given to, I guess, everyone, so you can look at the slides after the talk is over and have a very good idea of what our work is about. So when the paper eventually comes out, it'll be much easier for you to understand it. So they're kind of exhaustive, but I will pick some things in the results section, go to the appendix, and I'll show you the calculations of how things work. And the extent to which I'll do that depends on the amount of time that we have, okay? And then I'll conclude the talk. Right, so let's go to the introduction and motivation of the talk. So in this talk, okay, sorry, it's kind of busy, kind of wordy, but you know, rest assured you will see diagrams and they'll be easy to understand. So in this talk, we will explore the physics of this thing called the Hades-Witten theory and the Geyer-Monge theory. So these are the two different types of twists that you can have of 5D n equals to 2 gauge theories that are completely topological. Okay, and as per usual Yang-Mills, we are looking at Yang-Mills theories with real and compact D group G. But the key point here is that we will consider them on certain very specific 5 manifolds. Okay, so for our purposes, we have chosen certain 5 manifolds that are decomposable, meaning they're just product spaces of things. Okay, that's what I mean by decomposable in this here. Okay, so for generic 5 manifold, the analysis hasn't been done, but for our purposes, we need certain specific product manifolds. That's what we will consider. So what is the motivation for doing so? So the motivation for doing so is to unravel the dualities that might exist between these two theories. Okay, and of course, their mathematical implications. Now, what sort of set us or motivated us to study these two theories is because if you look at 5D n equals to 2, if you just compactify it on a circle, you get 4D n equals to 4. Okay, and that has your usual S duality and the whole Langlands story. So there must be something here that's going on if we consider at least one dimension to be a circle, for example. Okay, and if you topologically twist it, then reducing the size of the circle, you know, is in some sense in the homology or the BPS sector of the theory is invariant. So you have some kind of, you know, so we believe that there was some kind of duality going on there. That's one sub-motivation. Many years ago, Tachikawa wrote a paper of an untwisted theory of 5D n equals to 2 on a circle, cross M4, and showed an S duality in that situation. Okay, of course that was based on work by Vafa in geometric engineering, where if you had a circle that, you know, there was an automorphism around a circle, you can, map the gauge groups and that. So the point is that 5D n equals to 2 and S duality have a close relationship. And so we want to understand this a bit better. So that's one motivation. The second motivation is, if you look at the BPS equations of Hades-Witten theory, these are the equations that the topological theory localizes on in the path integral, and the GM theory, they look like an A and a B type of BPS equation. Okay, what do I mean by that? So if you look at worldsheet instantons in topological A sigma model, in your typical mirror symmetry kind of setup of sigma models, holomorphic maps, right? Okay. So if you look at the B model, constant maps. Now, these things, if you consider gauge theories, compactifying them on Riemann surfaces and coming down to get sigma models, that's a known thing that was done by Bershadsky, Sadov, Johansson many years ago. Kapustin and Witten used that method to get the results. You will see that worldsheet instantons or holomorphic maps come from instanton type of equations in the gauge theory. So Hades-Witten is some kind of deformed instanton equation. It's going to have F and a self-dual plus equals something else. Okay. Now the GM guy, okay, and then the constant map comes from flat connections in the gauge theory. And if you see the GM theory is BPS equation is a flat connection in 5 dimensions. So suspiciously, it is like an A and a B kind of model, but now in 5 dimensions and it's gauge theoretic. So that was kind of what led us to say, let us explore this to the very end and see what we can get at the at the very end. Okay, so that was what set us to try to understand the relationship between these two theories more. Suspected that they would reduce down to topological A and B model, and indeed they will, as I will show you later on. In fact, the 3D A model and B model. So of course, once we understand these dualities, we can try to extract the mathematical implications of this duality. Okay, so in the end, what we managed to do was the following. So we were able to demonstrate a physical duality between HW theory of G-type and GM theory of LG type. Okay, I will explain a bit more how you get this. But this only holds for that product manifold that we were talking about. Generically on an M5, we have not been able to, or rather we have not tried to show that, but certainly for this product manifold that we will show you what it is about, this duality exists. Okay, then what we can next find is a physical duality between a 3D n equals to 4a model and a 3D n equals to 4b model on mirror Hitchin moduli spaces. So how do you get this 3D n equals to 4a model? So this is a sigma model. So in our decomposable 5 manifold, there is a Riemann surface somewhere, and then we reduce the size of this Riemann surface. Same reasoning as the BSVJ reduction that Kapustin and Witten used. You integrate out all the gauge fields. When you shrink the Riemann surface, you end up getting a sigma model. And the BPS equation from 5 dimensions descends to the BPS equation in 3 dimensions. And this BPS equation in 3 dimensions is what we call the Floer map. So a Floer map is a 3-dimensional version of a holomorphic map. And if you go 1 dimension higher to a 4D sigma model, you get this thing called a Cauchy-Riemann Floer map. Okay, so, but constant maps will always be constant maps. On the B side, we get a holomorphic, we get a BPS equation that is a constant map still. Okay, now these guys are related to 2D models also at the hyperslides. I will explain. But the point is that we get this duality between these 3D models, and they are, the target spaces have to be mirror Hitchin moduli spaces. Okay, and mirror in that sense, what do I mean by mirror? So Hitchin moduli spaces, Hitchin moduli space of G is mirror to Hitchin moduli space of LG. So that was discovered by Thaddeus and Hauser and a few other people in a paper that predated Kapustin and Witten. That kind of motivated Kapustin and Witten to work out their story too. Okay, so we'll get this, second one. And then when we consider another permutation of this decomposable manifold, okay, of manifolds, of factors in the manifold, we can realize something more dramatic. We have what we call a Langlands dual mirror symmetry. Let me explain it. Okay, between Fukaya-Seidel A infinity 1 cat and filter A infinity 2 cats of G origin, okay, of G origin with, this is coming from the A side, the HW side, with Orlov's triangulated A infinity 1 category and Rosansky-Witten A infinity 2 category of LG origin coming from the GM or the B side, we call it. Okay, so you can actually get this. So this is what we actually get. Right, fine. So how does this sort of corroborate things that we know in mathematics or can make more predictions in math? Right, as I mentioned to Vivek just now, math to me is like a lab. Okay, we have results from physics and we try to see if it corroborates with what our math friends are doing in a more rigorous and exact kind of way and see if it all matches up. Okay, let's see. So this paper is kind of like more predictive than it is, verifying something. The previous papers were all verifying things, and it culminated in this, so we are making some predictions now. So if you look at what we said earlier on here, this guy here, from this one here, okay, the second one, filter A infinity 2 cat of G origin and A infinity 2 cat of LG origin. Now, so this is actually this is gauge theoretic. Okay, looking at this second guy here, So this physical duality between a 3D N4A model and a 3D N+4B model will allow us to actually furnish a physical proof of this conjecture by Bozu and Duan-Rechikov on the following, that they said there should be a duality between a filter A infinity 2 cat and a Rosansky A infinity 2 cat on a mirror target space. Okay, so this comes from this guy here. Okay, so by demonstrating this physical duality, we a physical proof of this conjecture that they made. Okay, so that's for this first point. And then if you look at, if you look at point 1, okay, where we have a duality between Fs A infinity 1 cat and Orlov's triangulated A infinity 1 cat. So this is actually, and then between G and LG, so this is actually a Langlands dual gauge theoretic generalization of homological mirror symmetry. Okay, let me explain what I mean by this. So where's the Langlands dual part? Okay, the Langlands dual part is that one is of G origin, one is of LG origin. Okay, so it's a Langlands duality. I'm going to say it's a correspondence. A correspondence is more than that. When I say it's a Langlands duality, I mean the group is G and LG origin. That's as far as I'm making the claim. Okay, correspondence involves other objects and everything. Maybe it lies inside here, but we have not unraveled that or discussed that. But the point is, Langlands dual in the sense that one is of G origin and the other is of LG origin. Okay, so that's the Langlands dual part. How about the gauge theoretic part? This A infinity 1 cat, the objects themselves are gauge theoretic flow homologies. Okay? Whereas in the usual mirror symmetry, they are branes. They could be Lagrangian branes, they could be coherent sheaves, holomorphic cycles that define coherent sheaves on the B side, for example, right? They are all submanifolds of some finite dimensional space, and their mathematical origins are not gauge theoretic. They are symplectic Floer in nature, or homological algebra in nature with extension groups and all that, but they're not gauge theoretic. But here, our categories as objects are gauge theoretic flow homology. So that's the gauge theoretic generalization of homological mirror symmetry. So the mirror symmetry part is an Fs relationship with Orlov's triangulated category. Okay, so that's the mirror part. So this part here is related to like coherent sheaves, the derived category of coherent sheaves in your usual mirror symmetry that you understand. Fukaya-Seidel, the Lagrangian branes, okay, from Fukaya and all that. Seidel because of the, it's a Landau-Ginzburg model, so it involves the timbals and all that. So that's the Seidel part, but the Fukaya part is the Lagrangian branes, okay? And the triangulated category here is the related to the derived category of coherent sheaves and usual mirror symmetry. So that's how we get a Langlands dual gauge theoretic generalization of homological mirror symmetry. Okay, that's what we mean by that. And then the BDR conjecture. So this conjecture here is about two categories. Okay, it's about two categories. And it involves usual sigma models and usual complex Lagrangian branes, the A, B, B, B type, and that kind of thing on Kitchen moduli space. So this is the usual one with two category mirror symmetry with these Lagrangian complex dash Lagrangian branes. But so in point 2, in our duality of 2, we have two categories whose objects are again gauge theoretic flow homologies. So again, we have, in the same sense, a gauge theoretic generalization of this BDR conjecture, and also Langlands dual because you have one of G origin and one of LG origin. Okay, so that's what words mean in the context of what we got in all these points. So they are in some sense a one-to-one kind of correspondence, right? So this one was the first point, and then these two are like the second points that we make. So these are the things that we would be able to make contact with math. These math conjectures are very recent, 2022, 2023. I think Bozo in his paper, in this paper, reference 1, he had a medal, he won a medal for that paper. Lots of very nice ideas inside. I would say it's a pretty visionary paper if you ask me. Yeah, so I like it very much. We like it very much. Duan Rachikov also. So these conjectures, and we are able to sort of give a purely physical proof of these conjectures. Okay, in your words, I'll show you the diagrams. Okay, so before that, so this talk is based on work with my student that is to appear, and is built on earlier insights by our previous papers with me and my postdoc and students. Okay, right. Okay. So, calculation methods, which I think I briefly went through or said just now. So we make use of this topological reduction of gauge theories to signal model by Bershadsky, Johansson, Sadov, and Vafa. This is also a technique employed by Kapusin and Witten in their paper. Okay, and then we make use of a Heegaard split. So this is math, of course, right? So a Heegaard split is a 3-manifold, and you can slice it at a Riemann surface and a Heegaard surface, and you can split it, and we make use of that math fact to get some of our results also. And then, of course, the third point is to recast our 5-dimensional gauge theories in terms of 2-dimensional or 3-dimensional gauge Landau-Ginzburg models, okay? So essentially, we are not compactifying anything here. We are just recasting the theories as a low-dimensional theory. How do you do that? So if you look at quantum field theories, and if you look at the action itself, say if you have 5 dimensions, it's like d5x. So what you do is that if you want to recast this as 2D or 3D, you will take d3x, okay, to be the measure of the action, and the other two integration variables to be part of the definition of the fields. And then you can recast your gauge theories in terms of a 3-dimensional theory, whereby the fields are now valued as those in the other directions they're not considering. Okay, so that's the physical technique that you can use to actually recast these things. It's the same like, for example, if you have a sigma model, a sigma model on a cylinder, right? And then if you look at the action, it's got a d sigma and a dt. So you could see, a string that's on a cylinder as a 1-dimensional quantum mechanical system that's propagating in the loop space of the target. Same kind of thing, right? So that is a prototype of how we can recast theories, quantum field theories in some dimension in terms of a quantum field theory in a lower dimension, okay? By changing the definition of the target space. Okay, so any questions at this point, even though they're just words, I'll get to the diagrams in a while. Yeah. Okay, so let's look at the two theories that we're studying. So this is the HW theory. It was first kind of described by Witten. I think it was a paper, Fibrines and Knots. Okay, so he kind of described it. He didn't really write it down, but he kind of described it. He described it in terms of describing the BBS equation. And at the same time, Andrew Hades he wrote down this set of equations that look like a 5-dimensional version of the Vafa-Witten equation. Okay, so he wrote down at the same time, and coincidentally, you had, in physics, Fibrines and Knots, that paper, you had a BBS equation that looks the same. So, and then Anderson wrote down the full action, and then we have this sort of formalized this theory. This is a 5D HW twist, we call it. It's defined on M4 cross R, specifically M4 cross R. Why? Because in the Hades-Witten equation, there's this thing called a read vector that you need to define, and therefore you have to select a direction that's preferred. So in this case, the authors of this previous work have all defined them on M4 cross R to simplify life. Of course, Zabzin and his collaborators have studied on generic M5. That makes it a bit more complicated, but nonetheless, we are looking at M4 plus R for our purpose. Okay, now this theory has a single scalar supercharge, meaning to say after you twist it, twisting just shifts the spins of the fields of the supercharges. Okay, and how do you do that? You essentially embed the R symmetry of the supersymmetry group into the Lorentz group, and that involves changing some indices on the spinor fields, and by group theory, you can see that they transform either as scalars or one forms. So there is a single scalar supercharge that you get in this theory, Q, Cal Q, and one can study the Q cohomology of this guy. So essentially what it means is that you're studying the BPS sector, the certain BPS sector of the original physical theory, okay? And this Q cohomology defines the TQFT. If you look at observables with respect to this Q cohomology inside the partition, inside the path integral, you can see that it's invariant under topological deformations of the underlying manifold. So we'll call this known as HW theory. And this TQFT is also balanced. So this is a very important point. What do we mean by balance? Balance means that the index, the relevant index of this TQFT is 0, meaning the virtual dimension of the BPS equations, the moduli space of BPS equations is 0, and therefore it means physically that the partition function is non-zero. Meaning, unlike say for the n2 twisted theory in Donaldson theory, the virtual dimension is not necessarily 0, and you have to insert operators inside to soak up the 0 modes. And partition function isn't always defined in that case, but here the partition function is non-zero, so it is defined. So physically what this means is that there are interaction terms in the action which you can bring down in the partition function that nicely absorb the fermion 0 modes in the measure, nicely. So this happens when the index is 0 or the virtual dimension of the moduli space of the BPS equation is 0. Okay, so this guy is 0. And that's because the Hades-Witten BPS equation is elliptic in nature. And so then you will have and it gives you a 0. Okay, so they look like this. The BPS equations look like this. Same thing in TQFT. You take the, to find the BPS equations, you set the Q variations of the fermions of 0. You have this. And these are, so if you look, there's an F plus here. So it's kind of like an instanton equation, right? So it's kind of like an instanton equation because you have F plus. So it's a deformed, and you can see it's like a 5-dimensional version of like the Vafa-Witten equation, right? Vafa-Witten also has the B mu V's here, and then they come in a commutator. So it's like a 5-dimensional version of that. Okay, and these are the fields. B mu V is actually an antisymmetric self-dual 2 form on M4. F is the usual field strength. A is a G connection. All this is still in G, okay, real compact Lie group. And T is along the R direction, which is the direction we take to be time. Okay, so this is the usual HW theory. So this is known. This is also featured in our previous work. Now this is less well known, okay, but it's from a pretty old piece of work that Gaia-Mosch actually defined. So they define this twist that is definable on any generic 5 manifold. There's no read vector in the equation because the equation is simply this, which is a flat GC connection. It's a complex gauge group connection, okay? So the connection is defined in this manner, basically. So the BPS equation for the GM theory is flat GC connections, okay? There's no read vector involved. They could have defined it on all any generic M5, but for our purpose, again, we are defining it on M4 plus R, okay? Again, single scalar supercharge. Let's call it Q hat. Same thing, Q cohomology defines the T, and just like HW, its partition function is non-zero because it is also balanced. Okay, so that's the point here, right? So many similarities, so we're beginning to see that we should be comparing these two theories. All right, so this is the mouse theory. Okay, now let's look at the results. I will summarize them in a diagram, and then we'll speak about the diagram, and if we have time, we'll go into the details of the calculations. Okay. No. So because it's complexified, not real. So this has two parts to it. It's not the real one. So it has like F plus some other thing. It's not the real one. It's not the real gauge group. Yeah. So it can be understood as this, but in the underlying theory, it is still, whereas the index is still computed with respect to G, basically. Okay, so that's the reason. Yeah, yes. Yes. Yes, yes. Yes. Yes, the two superchargers, the two homologies isomorphic. Yeah.
What ask you?
Right.
Which square to the Hamiltonian?
Yeah, I mean, you could if you want. Okay, so
For
what
now,
he
it's
said
like
is
Q1
correct.
minus Q2.
Actually, we have more than one scalar supercharge. We actually have two. Okay, so if you consider them independently, then they are, the two homology is isomorphic. But if you take the linear combination, you get something
Yeah,
else.
so in a sense, one can turn on this T parameter of Kaplan-Witten, right, to interpolate between the two.
Right. So
like
that is a possibility. So yeah, you're right. So it could be this. Okay, no. So this supercharge here, Q hat, is different from the second one that we got from the HW twist. So if you have a linear so you still need a second theory basically because it's a different one. The BPS equation wouldn't give you, it can't interpolate between this and the other one. It can't interpolate.
Yeah, but it seems like to be the 5D version of the interpolation between Kaplan-Witten equation with the flat connection for complex.
Yes, correct. That's in 4 dimensions for KW theory, right? That's in 4 dimensions for KW theory, right? So yeah, so in 5 dimensions you can't interpolate. Yeah, we thought about that because the other second supercharge, if we have a linear combination, it's still, the other supercharge still gives you the HW BPS equations. It doesn't give you the flat one. You can't interpolate. Yeah, in 4 dimensions you can. So the interpolation one, the story is in my work with Ashwin Kumar, where we had in 5 dimensions, you must start from a 5-dimensional n equals to 2 theory that is actually a topological holomorphic twist. Then if you reduce one circle, it becomes a 4D n equals to 4 KW twist. Then you can interpolate. In that one, you can. But if it's fully topologically twisted, you can't, because this Q hat here is a different supercharge from the other independent one, the dependent one in the HW twist, so you can't. So in short, the answer is the following. What you said of interpolation between the flat connections and the KW equations that you see in KW, where if you change the T, you can interpolate between the two, that would come from a 5D n equals to 2 topological holomorphic twist. Yeah. And the topological holomorphic twist collapses to a full topological twist in 4 dimensions when you reduce one circle. Okay, because the R symmetry group becomes less and the embedding becomes full and it becomes fully topological. From the understanding of string theory, the D4 brane, if you take the T duality down, then you also change the cotangent bundle that affects the twist in the world volume. So that's the answer. So in this case, if it's fully twisted, you can't. Okay. So Vivek, your question is valid. We have thought about this too. But when we find the lower dimensional, so this was a claim that they made and we find it kind of odd. Then we realized that the answer was that you're supposed to still compute the index like it was a real Lie group, because the original physical theory and the fermions that are in the theory are still defined with respect to a real Lie group. Yeah. No. The index of the operator acting on the fermions. Is different because the fermions, okay, see, because it's a twisted theory, so what should be spinors are now like 1 forms or 0 forms. That's the thing. It's like a twisted operator, basically. Yeah. Right. Okay, so in a nutshell, you know, the operators that are involved in the fermions acting on it, that dimension is 0. Okay, I don't have the details right now. We can discuss after this. Yeah, right. All right, okay. Okay. Anyway, you'll see later on that we will come down to a 3D theory that is also, the point is that it's consistent throughout this whole work that you do not need to insert operators inside the path integral to make it work. Okay, so that's another sort of justification for why it turned out to be correct. Okay. Okay. So this is the GM theory here. Okay. So let's look at our results. So he got split. Okay. So we had this, right? So we have not established this duality yet. Okay. We have not established this duality yet. Okay. So what we're going to do is that we're going to Higa split the M3 here at C. Okay. M1 can be anything for now. Okay. It could be S1, it could be R. Okay. We Higa split this. Now, once we Higa split this guy, the 5-dimensional manifold, is decomposed into 2 blocks. And on one block, we reduce the Riemann surface. We reduce it on the Riemann surface C. And because of that, we end up getting a 3D sigma model. But we have 2 blocks, basically. Right? But then these 2 blocks are meant to be joined together. But we have two 3D sigma models with branes, but they're joined together at the intersection, and we end up with a single sigma model with branes, actually, because it's an interval I here. This is a 3D A sigma model, and the BPS equation is a filter map, which is a 3-dimensional version of a holomorphic map. Okay? Now, so obviously, what we are looking at here is the Q cohomology. The Q cohomology survives this thing because it is a scalar supercharge. So regardless of what topological deformations you make, it exists. It has no direction and no geometry per se. Okay, so the Q cohomology here is captured by the Q cohomology here. Now, this is a topological field theory. So in any topological field theory, the Hamiltonian is 0. Okay, this being the time direction here. So the Hamiltonian is 0. So the Q cohomology are given by ground states, which are time invariant. Okay, so if you look at, so it suffices to look at the time invariant specialization of this guy to get our ground states, the time invariant ground states. Okay, the time invariant specialization of this action would reduce to a 2-dimensional action that lives on a hyperslice at R. Okay, so this is an old story. If you look at Chern-Simons in 3 dimensions and how WZW actually lives on the hyperslice of Chern-Simons, it's the same story. Same calculation in the action. You take your derivatives in T to be 0, you take your fields to be independent of T, and then you get a 2DA model here, okay, with the same target space. Okay, sigma model, 2 dimensions. Yes. There will be some boundary conditions, but what we are showing here is the duality first between them. Okay, so these boundary conditions are essentially what will give you these complex Lagrangian branes, basically, right? So this is a model in like a K in a K complex structure. So you have branes which are like star star A. I don't even know what I mean by yeah. So yeah, okay, right. All right. So and then for the Garamush, we consider the LG group. Okay, we consider the LG group, not the G group. Okay, we consider the LG group. We do the same thing. He got split at the C into 2 blocks, reduced on C, and because the BPS equations here, flat connections, we end up with what we call a B model, whereby the BPS equations become constant maps. Okay, and this is known as a, yes. No, these are the theories, basically. Yes, that's right. But we're looking at, yeah. Okay, so these dualities are all in the Q cohomology. So the Q cohomology is a vector space, right? Yeah. Okay, so these dualities of these theories are all restricted to the Q cohomology of the theories, and that's a vector space. So we have a duality of the Q cohomology and therefore a duality of the vector spaces associated with these theories, the names of these things. Okay, right. Okay, so we have a B model here, okay, but because we started with LG, then the target space is LGC. Same reasoning as just now, this is a topological field theory. So given by ground states which are time invariant, if you look at the time invariant specialization of this guy, it's actually a 2D theory that lives on a hyperslice on R, and it is a B model, basically. Yeah. No. Yeah, so that's what I'm going to explain now. I'm not finished yet. Yeah, because the squiggle is going to come here. We're going to make an inference, basically, an inference. We're going to make an inference. So this guy is dual to this. This is known. Okay, it's known. Now it's formalized by Thaddeus or Hauser, I think. It's called enhanced homological mirror symmetry. Okay, but Kapusin-Witten is this, basically. Yeah. Okay, so, I mean, there's this thing called enhanced homological mirror symmetry. Hauser, right? Hauser wrote a paper on that. So what's this enhanced homological mirror symmetry? Do you know? No, you can look at the reference. That's what, I mean, in this paid reference itself, you know, it's meant to sort of give what Kapusin and Witten did a rigorous definition. Okay, anyway, Kapusin and Witten, we all know this is true. Right? I mean, this is true from physics anyway. We know it because this is a mirror, this is a mirror. We have an A model and a B model. Okay, fine. So that's known in physics, right? Of homological mirror symmetry from the old days in the mid-90s. So these guys are dual, and these guys are related, which implies a duality between these guys, which then implies a duality between these guys. Okay, so to answer Pace. That's right. Okay, so not just that, I mean, you have mirror symmetry of hypercale. No, okay, so we don't have a T parameter. Okay, so we don't have a family, but this is one point on P that will give you this. Nice. Right, okay, so we understood it as well from the paper that it was also involving branes that are not just A and B, but complex Lagrangian that can be A, B, B, and all that. That's what we understood from that paper too. So two things, like you said. First, the P, which is a family of topological twisted theories. Second thing is that no, I don't have a P1 inside because I don't have a parameter T, but this is for specific value of P1 in Kapusin-Witten and in what? Yeah, so it's enhanced in this sense is there's 1 point in P, one point in P1, and the fact that the branes are not just your usual A and B branes, but they are a mix of A, B, B, A. Okay, so that's what we mean by that. Okay, so that's in that paper, and they claim that this is going to be a rigorous. This is A in K, B in J. So here the branes are star star A kind, and then here you have star B star. So that can, right? So this is the usual mirror symmetry. Not usual. This is the mirror. Okay, right. So this term here, it was from, what we're trying to say is that the math people who try to rigorize what Kapusin and Witten found, and we're just using this thing so that math people like you could be familiar with what we're saying. That's it. If I was a physicist, which I am, I'll just leave this out and say the usual mirror symmetry that we understand. So I'm sorry that's causing all this confusion. But to answer your question, if it's a P1 worth of twisted theories, it's one value that gives you A to B, right? Okay, all right. So that's how we imply the duality in 5 dimensions. So you can see that the manifold type is important. It can't be just on any generic 5 manifold that the 5D theories are dual. So that's how we deduced it from bottom up. Okay, so that's how we deduced it. Okay. Now, if we take M1 to be R, here, as you can see, same Q cohomology. Yes. No, because all we need is a Q cohomology. Yeah, what we are focusing on is the Q cohomology. Yeah. I mean, a quantum field theory is much richer than the Q cohomology, of course. Much, much richer than that. So we are looking at the Q cohomology. For mathematical applications, Q cohomology, for our mathematical applications, the Q cohomology will suffice. So we're looking at that and the Q cohomology of that Q itself. Right. 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 So no, we are looking at the action and we are taking a time invariant version of the action. We are saying that the Q cohomology are time invariant states, so they should be captured by the time invariant part of the action also. And when you take the time invariant part of the action, you take the derivatives of t to be zero. It's a relations. It's a dependence on t to be zero. It's the same story of the WZW and the Chen-Simons one. Yeah. So we are looking at the time invariant part of the theory. Okay. Yeah. So so that's captured by the hyperslice itself. That's the gauge theory. This one is not a gauge theory. So this is much simpler actually. Yeah, that one you're gonna impose the gauge and all those things. This is much simpler. It's just taking del t equals to 0 and the field is not independent of t. That's it. Yeah, very easy. This one. Right. Yeah. Okay. So let's continue. Right. So okay. So we have this guy here. So now we take the M1 to be R, and then this becomes R2. And then we rewrite this guy here as a 2D Landau-Ginzburg. Okay, in the space of fields on M3. And when we do that, in our earlier work, we were able to show that this 2D Landau-Ginzburg, the worksheet of the Landau-Ginzburg, the worksheet of the Landau-Ginzburg is actually a soliton worksheet. You have a soliton at the end, you know. Right. He conjectured this, and we proved this physically. He conjectured these ideas. That's right, you're right. So this was conjectured by Hades, and this was done in our very first paper leading up to this time. We had 4 papers on this. This was the first paper that we wrote. You're right, absolutely. So it was Hades who actually conjectured it. He has sketched how this could be true. Exactly, that's the thing. That's the one. So it was FS cat, where the endpoints of the objects are these GC instant-on flow homology. Okay, so we repeat this for the GM theory of LG, and then we get this guy here. Okay, so it's a B Landau-Ginzburg. So we have a B twisted Landau-Ginzburg here, where we actually recast this on R2. So the difference between the A twist and the B twist is that the BPS equation is slightly different. On the A twisted side, if you look at the BPS equations on Landau-Ginzburg, one side gives you the derivatives and the superpotential. On the left side, it's like a holomorphic map. So the B one, on one side is a superpotential, derivative of superpotential, the other side is like a constant map. Okay? And then the categories that you get because of this difference in the BPS equation is what we call an all of A infinity 1 category. Now, the flow homology that you get at the endpoints is something quite exotic. Okay, it's a flat flow homology, meaning to say that the usual one, when we say instanton flow homology, we mean the following. You have M3 cross R, an instanton equation on M3 cross R, and then you get some flow homology on M3. In this, yes, because I know, right? Yeah, so this space is a space of all fields on M3. So it's something, it's a gauge theoretic version of FS. Space of all quantum fields that are involved in this theory here on M3. Basically. What do you mean? Which function are you talking about? Like, yeah. So yes. I'll show you the function in a while. Right. You're talking about the Morse function, right? You're talking about the Morse function. Are you talking about the Morse function? Yes. It can be shown. Yeah. I'll show you the Morse function and all. So the Morse function for this guy here, I'll show you the Morse function later on. Yes, yeah. That's right. So the function I think you're saying here is the Morse function, right, of this guy. Yeah, it is the Morse function. The space here is the space of all fields on space of fields on M3. Okay. Same thing, the space of fields on M3. Okay, right. So the space of fields from this guy here, this LG flat refers to the Floer homology, not the LG flat fields on M3. No, no, no. Okay? Yeah, the space of fields on M3. And then the critical points of this Floer homology are these fields on M3. So the space that you're talking about is cat here. Okay, I'll put it in. So the Landau-Ginzburg model on R2 has a target space. No, 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 no. Okay. So this is a Landau-Ginzburg gauge Landau-Ginzburg model. This guy here refers to the endpoints of the soliton. The endpoints of the soliton, which are critical points of a function. Got it? Yeah, yeah. So this is a, I guess, translational issue. So these are the endpoints of the critical points, endpoints of the soliton given by critical points of the function. Okay, right. All right, so we have this here. Okay, so if you do this, so you can see that this is the gauge-theoretic version of the usual homological mirror symmetry between Landau-Ginzburg models, whereby the endpoints themselves are the branes. But here we have endpoints being gauge-theoretic Floer homology. So it is gauge-theoretic in this sense. Okay, so it's a gauge-theoretic generalization in this sense. And we see we have an LG and a G. So it's Langlands dual in this sense. Okay? Okay. 2 more minutes. So, and then the same thing, if we take, what we did just now, we cut we Higa split this guy, and then we end up getting a 3D sigma model of A type. So this is what we have here. Okay, and this is just the BDR conjecture. Okay, so the BDR conjecture is for a sigma model whereby the world volume is interval cross R2. So that's when we took M1 to be R, and then you can have an interval cross R2, and so we have the BDR conjecture. Okay, we made it concrete by taking M1 to be R. Okay. Then you take M3 to be M2 cross R. Okay, we have the third one, R3. Okay. And then same thing, we have a duality, and if you give us a 3D gauge Landau-Ginzburg model, 3D. So once you have an extra direction, you can think of the 3D gauge Landau-Ginzburg as a 2D Landau-Ginzburg that is translated to another 2D Landau-Ginzburg. That gives us the additional higher categorical structure, a Hom of a Hom, basically. Okay, so that's what it means. It gives us a Hom of a Hom. So here we would have a 2-cat where the very basic objects, the two objects themselves at the end of one of the solitons on a sheet would be given by this guy. Okay, so it's a Floer homology whereby the 3-dimensional equation that defines it on M2 cross R is 3DGC monopole. Makes sense? In Synton, you reduce by 1 dimension, you get a monopole equation. Okay, so it's consistent, it makes sense. And then likewise, for the GM theory side, you get a Rosansky return A infinity 2-cat that's associated with a B-twisted Landau-Ginzburg model in 3 dimensions. That's right, absolutely. That's right. Yeah. This always defines the M2 cross R, M3 cross R for the Floer homology. Right. Okay. And so we have this. Okay. So I didn't have time to go into the details of it. The slides are available. If you click all these things here, you will see the details. I'll give you an example since I just have maybe 1 minute. So like if you click this guy here, for example, it goes to the appendix. Okay, so and then it gives you all the gory details of things. they're, they just involved, but they're straightforward. Okay, they're pretty straightforward. All the things that you want, your functions and everything, they're all here, basically. Okay, critical points of this most functional, they're all here. Yeah, you can see for yourself, they're all here. And okay, so this defines the A infinity structure. You have scattering of soliton membranes, basically. Okay, and then, okay, so the solitons are here, the objects are at the vertices, basically. Okay, so you can see that there's a Hom of a Hom kind of structure going on here. Yeah. Okay, so for example, right? You can return to figure 3. Okay, so I believe the slides will be provided, and so you can click off the red ones and you can see all the details inside. And yeah, since I'm out of time, so I guess Vivek gave us a lot of questions. Anyone else has questions? Oh yes, question time. Question time. So question time is 5 minutes from now. All finished. 10 minutes from now. Okay, great. Okay, I can use the question time. Okay, I have 10 more minutes. Then let me just show you some of the details of the calculation, right? Okay, so let's do that. So let's say this one here, yeah, like this. Okay, so if you Higa split the guy, you got 2 blocks of the M5. You reduce a C along this N5, you get a 3D sigma model with branes like this. But obviously, we're not really splitting the manifold, so these 2 boundaries are actually identified. Okay, and then you effectively get a single 3D N+4 sigma model with branes at the side here. And to answer your question, what kind of theory we have, it's on the A side, it sees the complex structure of K in the target space. On the B side, it sees the complex structure of J in the target space. Okay, right. So this is how we are doing split. These are just some words of things that I've already said. Okay. And then the hyperslice one, okay, just some description of it. Okay, so if you simply put, if you just take you look at the 3D action, look at the time invariant specialization of the 3D action, it collapses to a 2D action that lives on the hyperslice. And that's how we can make the connection to a 2D sigma model. Yes? Okay. Yes. Yeah, because once you split, first interval, second interval.
But what is the I that you had in your diagram?
Normal interval. So what's going on is this. When you do a Higa split, this part here can be seen as a C fibration over the interval.
Yeah.
Then you can do a Vauri scaling of the metric to make it into a product space. Then becomes C cross I. That's why you can see C cross. If only because it's topological theory. If it's not topological theory, you can't do that.
No, what confused me is that you have 2 sides, right? You have an I prime and an I second, but you seem to have only. So you pick one of the 2 when you do this diagram.
Sorry. So you mean I prime and I double prime?
Yeah.
One belongs to this, one belongs to this.
Yeah.
So by right, they are together. So I'm just showing I prime and I double prime to show that this is the interval for this guy, this is the interval for this guy. They are both I, basically. Topologically, they're just interval, basically. It's just naming the left block and the right block. That's all.
Oh, I see. So I is like the union of the 2.
Yes, correct. I is the union of the 2. Correct. Okay, so I is the union of the 2 intervals, one to the left block, one to the right block. Yeah, okay. It's very easy. It's nothing complicated. Yeah, very easy. Yes. Okay. All right. So let's look at something else. I still have some time, right? Yeah. Okay. I still have some time. 5 more minutes. Yeah. Okay. So okay. So maybe we look at this guy here. Okay. So the all of category 1, right? Okay. So we basically recast the Langlands-Ginsburg as a model on R2 in the target space of all of the quantum fields on M3. Okay, and then you get a BPS equation that looks like this. We can recast the BPS equation into a GH connection, basically. Okay, so this part here is I guess the slightly not so straightforward one, but it works out. And then when you do that, you can recast the BPS equation this way. Quaternionic. So just like A plus IB is complex, now we have like this guy here, like that. Two of such fields, which is, this is like A plus I phi. This is like C plus ID. And then we write it like this, and then we can recast our PPS equation in this way. So that's the thing. We didn't see this, until recently. Then we realized that if we were to recast it this way, then we can write it in a form that's familiar, obviously. So that's how the quaternionic kind of structure comes in. So I would say this is a nice surprise that we found, basically. So you don't see this. I mean, this is the first time we have tried to see if people have studied GH connections, but no, this is what from us, basically. Yeah. Okay, so yeah, and you can see this is your 2D gauge Langlands-Ginsburg, but it's the B type, because if you look at this equation, this is like a constant map. If it's a holomorphic map, it looks different from this. Okay, right. So this is the B type. And then the space of fields, the space you're talking about is frac A3 here, space of fields of A and B on A3 basically. Okay. And then you can see that you can recast this 2D Langlands-Ginsburg model as a 1D quantum mechanics on the space of half space, basically, this guy here. And then the usual quantum mechanical analysis will tell you that the critical points of the SQM would be given by these guys. Now, these guys define a soliton on one edge of the worldsheet. Okay? And the interesting thing is, and then the potential function is this. Now, look at this. This also defines the gradient flow equation for flow homology. So this is a soliton equation, but it also defines a gradient flow equation for flow homology, such that when you have like a soliton here and its endpoints here, there's a gradient flow equation like the one that defines the flow homology. And your space is that frac A3. Okay, and the function is this guy here. Yeah. Okay. So it's like a BF kind of function. Critical points of this guy give you the endpoints of this guy here. The endpoints here. Okay. So, and this is a soliton worldsheet. And you can consider the 3-level scattering of the partition function. Okay, now that you have a effective 2D Langlands-Ginsburg model. And the composition map that defines A infinity, and because it's a topologically twisted theory, you only consider the lowest 3-level scatter. And we have this mapping of the HOMs. The HOMs here are just like the soliton itself. So this guy here are the ends. The H here is the Hilbert space or the vector space of homology. Okay, so a vector here, and then it maps. Right? Okay. So that's pretty much what the all of triangular category is. Okay, so the one thing that I want to mention is that the ends of the soliton, they can be described by the fibers above the W plane. Okay, so in the case of Gato, Moore, and Witten in algebra of the infrared, that was an A type of Langlands-Ginsburg, and so they were described by thimbles at the ends. But in the B type is described by Orloff's singularities, the singularities of the inverse map of the superpotential of the zero locus. Okay, right. Okay, right. So, okay, I guess yeah, my time is up. Okay, all right. Thank you very much for coming. Yes.
Speaker,
Thank you. Yeah.
any more questions?
Yeah. Moduli space of, okay, they are not moduli space of monopoles. It's a space of figurations on M3 that at the ends of the soliton are precisely the values that satisfy the monopole equation. So it's not the moduli space, but one point on it basically. Okay, so the space in the Langlands-Ginsburg, okay. Yeah, right, that's right. This one, right? Yeah, right. So this equation here is this equation. Okay. Yeah. Right. So the monopole equation is essentially this guy here, translated to the three manifold with this thing here. Yes, correct. It's M2, yeah, curve MR. Right. The fields decay to zero physically. Yeah. The fields decay to zero physically. That's the boundary condition at infinity. Yeah. Any more questions? Yes.
So if I reduce 5D theory on Riemann surface,
Yes.
so there are like these M flat directions.
Yes,
But
that's
then
right.
there's also a direction parameterized by dual photon, right? So is there a way to argue that they somehow would not contribute to the story? Because it's not.
Okay, so what we did was BSVJ in that sense of taking the metrics and scaling it, and then taking the looking at conditions and make it finite. It's exactly like BSVJ.
Yeah, but BGSV is like reducing 4D theory, so they're not having this kind of problem because dual photon is only like in 3D, right?
Right. So yeah, it came out as the components come out as scalars that we have to take into account. So we have to take into account the components as scalars, basically. You're talking about the directions of the gauge field initially, right?
Yeah, so the gauge field in 5D also reduces the gauge field in 3D.
Yes, that's right. So the other components all come out as scalars, basically. And we have to take into account those things.
In addition to those,
Yes.
there's also dual photon, right? So there are going to be more scalars.
Yes, almost yes. That's why the GH and the GO comes about. There are a lot of them coming out, basically. Yeah. So the reason we saw a GH, right? Like say the Gaia Meng-Chwan, the GH that we saw, that's because of all these things that you talked about. Yeah. So they were all sitting around, and then we realized that we could repackage them into GH or G0 to make the flat connection that you saw just now. So these things were sitting around, like what you said, basically.
Okay.
Yeah.
I thought the model space would be more complicated, but maybe somehow the other direction would not contribute in a meaningful way.
You mean the moduli space is more complicated than just the Hitchin moduli space?
Yeah, it's way more complicated, right?
Not really. I mean, we look at the terms which.
So let me maybe just give an example. If you consider E8,
Yes.
then in the model space, you not only have E8 Hitchin model space, but also A8, D8, or all the other things. They are connected by like.
You mean the E8 gauge group, basically?
Yeah.
Okay, right. So we are considering, okay, we are taking like generic gauge group G here. By right, it should work for exceptional, but we didn't look at the exceptional case, basically.
But even for other things, there are like other maximal supersymmetric superconformal points. So like that's like one difference between the 5D theory and 4D theory.
Right.
So the BGSV via the 4D theory only capture one superconformal theory on the model space of the 5D. But there are other.
Yeah, sure. But we have twisted the theory, right? So it's we have twisted the theory. So so we are not looking at any superconformal point. We're not changing the energy scale, basically. We have twisted the theory, basically.
Yeah, so I think that's exactly what this story is about. It's still like somehow describing some part of the.
Yes, not the whole thing, Yeah, only part of it. Yeah, I mean the whole analysis is of course much more complicated. Of course. I mean, if you were to look at it, if you were to see as a conformal theory, then it's more complicated. Of course. Yeah, the topological theory is just the simplest, lowest energy states of the theory, and then these things that you see, the spaces and all that, would apply to these. But like what you mentioned, if you were to do a more careful analysis that's not topological of the, if not even the full theory, even the superconformal versions of it, then of course it's much more complicated.
Yeah, I would argue like even for topological theory, there are ways to have those to contribute, but of course there might be some truncation that.
Yeah, right. So okay, so I would say, okay, what I can say is this, so that maybe we can get to the answer. Okay, so in those directions that we reduce, certainly we have scalars coming out from the gauge fields. Okay, there were a lot more scalars than we expected, but we were able to package them into a GH or GO connection, as you saw earlier on, and then it all worked out. As for the moduli space as for the target space, the target space again is from the same BSVJ way of arguing, which is that the action needs to remain finite. And so those things that you need to set to 0, those terms still give us the usual Hitchin moduli space terms. Yeah, so nothing more than that. So that's how the moduli space is nothing more than the Hitchin moduli space, right? Yeah. So of course, I mean, then in the end we do get these results with corroborate with math. So as you said, there could be some truncation which works out in this scenario. Yeah, but if you were to study the whole thing, maybe there's some other subtleties, perhaps. Yeah. Okay.
Okay, let's thank the speaker again.